Hey everybody, and welcome back to the Protocol Town Hall. This is our 2025 guest talk series, and it is the end of the summer part of the series. We have something new in store coming this fall, which should be interesting, including potentially a guest host. Today's guest is Shreya Shankar. She is a PhD student at UC Berkeley and has made waves with her DocETL work. Um, She's in her final year of her PhD and will be on the 2025-2026 academic job market, so watch out. She's specializing in data systems and foundations, and her research is supported by the NDSEG Fellowship, compute credits from Modal Labs, and sponsors of the EPIC Lab. Before her PhD, she worked as a machine learning and data engineer at a couple of startups, and before that, did an undergrad in computer science at Stanford University. So right now she's developing query optimization algorithms and is here to talk to us about her research and a roadmap for where that is going. Welcome to the Protocol Town Hall, Shreya.
Awesome. Thanks, Timber, for having me. Just a question for you. So are questions going to come at the end? Are they going to come periodically? Do you want to ask them? Am I speaking to the
Well,
void? Kind of what is that going to look like?
speak to the void. There are going to
Okay.
be, roughly 30 to 40 people in the void. And the way we typically do it is people will put questions in the chat. I'll bring them up on stage at the end and we can riff on them a bit towards the last 20-ish minutes.
Perfect. Sounds great. Awesome. Well, thanks for having me. I'm Shreya. I am a final year PhD student at UC Berkeley, as Timber mentioned, and I will talk to you a little bit about our DocETL and various other spin-off projects that have originated from it. So I want to start out by motivating a pervasive problem we've had for pretty much the last several decades in data management is making sense of unstructured data. And this is pervasive throughout kind of every single industry out there. There's lots of unstructured data, think PDFs, documents, transcripts, any long form text. And this is very difficult to make sense of with relational databases. So when I say relational databases, think something like SQL, like Postgres, MySQL, SQLite. You can't really express the kind of complex queries that you need that require some sort of semantic understanding of the data in them. But now we have these beautiful large language models and AI systems that can kind of understand our intent and try to execute queries on the data. So to give you an example of something that we're working on pretty much right now with public defenders in the state of California, they have a bunch of police records, police reports, and they want to figure out if there are unjust sentencing enhancements that are hidden in these free-form notes fields. So for example, maybe they found a weapon at the scene. If they can tie the weapon to the defendant and say that the defendant used that weapon to threaten someone else, they can increase the sentence of this defendant. Now, of course, there's some legal interpretation there. And I'm not a legal expert, but these public defenders want to figure out, okay, did something kind of unfairly get added, an enhancement unfairly get added based on their race, which would violate the Racial Justice Act. And so this is kind of very high stakes for people. There's potential for incorrect life sentences. And I'm not here to kind of talk about this problem in particular, but I want to give you a sense of the meaty, of the rich problems that people really face on a day-to-day life with unstructured data. And I have problems that we're working on kind of in medicine, in law, in all sorts of fields. So I mentioned large language models maybe can come to the rescue to help us solve these kinds of queries. And we're calling this paradigm, it's not just us, a bunch of other people, folks across Stanford, across MIT, calling it semantic data processing. And the idea here is to use familiar data processing operators. So if you're kind of familiar with data pipelining like Spark or Pandas, or even relational databases, you can use these data processing operators, but instead of writing like a function to do each one of these filter or reduce operators, we can have a large language model take in a prompt and execute that operator. So I know that sounds abstract, but a concrete example of this is, say you have a map operator, it reads a free-form text note. An LLM essentially executes a prompt of your specification and tries to extract some structured information out of that document. So for example, maybe we want to figure out, who is the defendant in this report? Was there a weapon? Do we know whether it belonged to the defendant or not? So we can do this at scale with a large language model. And then we can even chain these complex operators together. So for example, you could also add a reduce to maybe group by the defendant name, run this pipeline on a very, very large set of documents, group by the defendant name, and then summarize, all of the information that we've extracted. So you don't have to get into the details, but the high level takeaway here is now semantic data processing allows us to query and transform data based on its meaning, which is very powerful for unstructured data analysis. So a lot of my research over the last couple of years has been focused on, okay, how do we reimagine the data stack or the technology that we need to build these tools? And we look at relational databases kind of as a blueprint or a way to think about building this new stack for unstructured data processing. But what's exciting about unstructured data is that now we have new components and things that we care about in data processing. For example, in our query optimizer, in traditional databases, query optimizers just make queries run really fast or very cheaply. Right now our queries are somewhat approximate. They might be incorrect, right? Because large language models are executing them. So now we have to optimize for both cost as well as the accuracy or quality of the outputs. Another interesting challenge that we've run into is, okay, people are writing these pipelines, but they don't really know what they want to write, what prompts to write. They don't know what's going to work well on the data, what's the LLM going to understand. So you need this kind of playground layer on top of the interface to help people prototype with and experiment different pipelines. These are just an example of two different new things that have arose basically from unstructured data. So in today's talk, I'm going to kind of go over both of them. One being DocETL, a new optimizer architecture that we've come up with. And then the other one is DocWrangler. And this is work that I'll actually be presenting in a couple of weeks at UIST, which is an HCI systems conference. So let's start with DocETL. We launched this system for unstructured data processing about a year ago, almost a year ago, which is crazy to think about, and we're still actively writing code for it. And the things that you should know about the system, other than it's open source and getting a modest amount of traction, is that we offer a no or low code interface to be able to prototype these pipelines. And we also offer an agentic optimizer. And so that sounds fancy, that's pretty new, but the idea here is we figure out how to rewrite pipelines that users provide us with to have better accuracy under the hood. And excitingly, we've been able to get some traction in lots of different domains. But I'll tell you about what motivated us to start this project in the first place. And it's actually very related to the public defender use case that I talked about earlier, but public defenders came later after they heard about DocETL. This around 2023, I want to say, or late 2022, actually, there was a team at Berkeley that was comprised of law school people, School of Journalism people, and data science and database people, all trying to figure out, how are we going to create a database of police officers in the state of California. They got a very big grant to do this, and they collected a bunch of police records from the state of California, and they wanted to figure out, okay, can we create a database of all of the misconduct that police officers have exhibited? And I don't want to be political about this. I think this is just a very fascinating data management problem, right? Because you have terabytes, sometimes even petabytes if you include images of unstructured data. And the goal is to really get this very structured table with high accuracy of police officers and summaries of their misconduct that you can glean from the case reports as well as transcripts and whatnot. And there's a lot of challenges involved in this because you need some sort of reasoning or AI expertise to figure out, okay, what did they exhibit misconduct or not, what type of misconduct, so forth. Often there's cross-document analysis, it's not so clean and crystal clear. Police officers might be represented in all sorts of cases, might be in all sorts of documents. There are many documents that pertain to a case. Nothing is perfectly labeled, right? So it's this big mess that you have to turn into this table. And there are no great approaches to do this prior to LLM. So people were trying to do some sort of manual review, get law student interns, train their own custom models, which was very resource intensive. They were even trying to use large language models to do this, but these are very error prone and hard to program. So this kind of motivated, okay, we need to build a system that helps us automatically find higher accuracy pipelines. But the challenge here from the systems point of view is it was not clear to us how we were even going to find higher accuracy pipelines. We didn't even know what made for good accuracy or not. We just knew if we looked at outputs from LLMs that they were kind of wrong. Like you could vibe check them and figure out they were wrong. For example, LLMs might ignore instances of misconduct if you ask, for an LLM to extract all instances of misconduct from a document. And this is known in the literature. People know that, for example, in middle of documents, LLMs are less good at solving tasks in there. And this required people to manually verify and people to figure out, okay, if this doesn't work, we have to figure out how to decompose the task into smaller scoped operators to be a little bit more reliable. So first, what we thought is, okay, maybe the LLMs are going to get better. Unfortunately, we read a bunch of research and we realized that LLMs are always going to make some amount of mistakes. Can't always be perfect for every single task. So we thought, okay, if we're going to build an optimizer to get us better accuracy, the key insight that we had as kind of experts who were building these pipelines were that you could get better accuracy if you took a complex task and broke it down to smaller scoped tasks. So LLMs could just focus on small pieces of the problem. So when we tried to do this ourselves manually, say we have an operation like extract any instances of misconduct from this document, just a map operation if you're kind of familiar with DocETL. Rewriting this pipeline to have better accuracy was not very straightforward to us. So for example, maybe you could split this up into two different map operations. One of them that first extracted any police officer names, and then the second one is just focus on particular police officers and then extract instances of misconduct for each police officer. So that's one way to do it. You kind of split along the task axis. Another way to do it is split along the data axis, as many of these documents were like 200 plus pages long. So maybe we could split the documents up into chunks or like groups of 10 to 12 pages, and then run that same prompt on each subunit of the document. Maybe you could do some combination of both, right? You could do some maybe I will extract police officer names and then I will just fact check them against a database of police officers that I know exist. And then I will go try to extract instances of misconduct. So all of these things we're doing, right? All of these seemingly ad hoc ways of rewriting the pipeline to get better accuracy. And so from a systems point of view, if we want to automate this process, right, it's not clear how to do it, right? You don't know from looking at this which plan is automatically going to be the highest accuracy. And you don't know, for some of these plans, there are parameter choices that are required. For example, if I take a long document and split it into chunks, what is the chunk size going to be? Like, how am I going to decide to split up the documents, right? This is also unclear. So hopefully I have motivated throughout all of this, these first 10 minutes or so, that A, unstructured data processing is a hard problem. B, we can use LLMs to do it, but we don't know if they will be accurate. And then C, how to rewrite for accuracy, even though we have some sort of ideas. It's unclear how to actually do this at scale in an automated way with a system. So that is going to be the focus of the next part of the talk. To talk about how we do this automatic accuracy optimization, first I have to talk about a little bit of the operators that we introduce. Then I will talk about our optimizer secret sauce, which we call rewrite directives. And then I'll talk about the system architecture that we use to actually go and try to employ these rewrite directives. All right. So in DocETL, we have a bunch of operators. I talked about map, reduce, and filter. Turns out that there are more. I won't go into all of them in great detail. We also have added more since we open sourced, so it's not in the paper. And I'm sure there will be even more that we add in the future. We have some non-LLM-powered operators, which I'll talk about as well. And these are all kind of no-code YAML-based operators. At least you specify the pipeline in YAML. Now, the operators that I want to talk about here are the resolve operator and the split and gather operators, because these are new. Traditional data processing systems don't have them. We need to have them because we're using LLMs. And I'll talk about why for each one of these. So the resolve operator, and is new for our system, and I think broadly is going to be like a primitive in pretty much all LLM-powered data processing systems. But the idea here is that when you do try to kind of extract things from documents, group by the thing you want to extract and do analysis, LLMs are inconsistent. So first, data is inconsistently referred to, or sorry, people are inconsistently referred to in documents, sure. But even if you have an LLM extract the officer name, and then when you want to group by officer name, LLMs are inconsistently going to extract, and we see this all the time. Sometimes it extracts a first name, sometimes it extracts a first and last name, sometimes it's officer last name. And you can specify in the prompt, hey, you want this exact format or whatnot, but you have no control over whether the LLM is actually going to listen to that. And if the first name and last name aren't represented in the data, then the LLM might hallucinate a first name or a last name. So basically, you're going to get inconsistent extractions. And so when you group by something, you need to somehow do some entity resolution or dedupe these entities, semantically dedupe them before doing the group by. So our resolve operator does just that. From a data systems perspective, it's an interesting operator because it requires basically naively pairwise comparisons over all of the entities. So we try to optimize that by kind of pruning away comparisons that we believe are not going to be true, kind of scheduling these interestingly. Talk about that if people have questions later on. But the way that the interface works is that the user specifies a comparison prompt to tell us whether two entities are the same or not. So this is a natural language, yes or no like question. And then a resolution prompt, which basically we apply to entire cluster that we've determined to be equal based on the comparison prompt. And that gives you the canonical, for example, officer name, or the canonical entity to then group by and refer to later on in analysis. So that's resolve. The other two operators I want to talk about are the split and the gather operators. Again, these are operators that are not in traditional data processing systems, but we need to have them here in DocETL because they enable interesting rewrites later on. So split operator is kind of how it's self-explanatory in some way. You take a document, you split it up into smaller units. But now the challenge of operating on these chunks individually is that sometimes you can't make sense of a chunk in isolation. So for example, if I look at the second chunk here, I don't know who is he. I don't know what happened before he then proceeded to do something. And for that reason, if I have an LLM trying to do a map operation on just the second chunk, then it won't know what to do. Right? You need some sort of information from the preceding chunks to help to give the LLM context. So the gather operator kind of allows us to flexibly kind of retrieve context to make sense of the chunk that the LLM is currently trying to process. And there are all sorts of ways you can come up with this relevant context. For example, you could imagine like a sliding window. So for example, previous or next chunks are very useful for like context that's useful to make sense of a chunk. You could imagine maybe an entire summary or transformation of all preceding chunks. You could imagine any metadata from the document. This is something that we see a lot. Sometimes documents will have like a table of contents in the beginning or some sort of headers or metadata that's very useful for making sense of the any chunk in the document. So you kind of want to pin that as context necessary to process any individual chunk. And in the paper, we talk about some ways to actually configure this, how flexible it is, how you can specify it in YAML, so forth. I won't get into that here. But the point is, I think any kind of semantic data processing system that's trying to kind of decompose and rewrite pipelines is going to need some equivalent of a gather operator. All right. So those are some of the operators that we have at a high level. And so now I can talk about how we rewrite these pipelines to be even more complex but smaller scoped operators. We try to do this automatically. So at a high level, we define what we term rewrite directives. Now, this is going to sound abstract, but hopefully when I give you examples, it'll be a little bit more clear. So we define what we call rewrite directives, and these are simply templates for how someone might break down an operator or a sub-pipeline into something more complex. So for example, if I have a map operator, so map is just think of like a function, right? One-to-one operator operating on a document. I could rewrite that map operation into first a split operation that splits the documents in the chunks, gather operation that augments each chunk with relevant context, then a map operation that can be applied to each individual chunk, and then finally a reduce operation that takes the result of each individual map, and then hopefully gives me something equivalent to what I wanted in the first place. So now this is kind of the key insight here, right? If we can define these reliable ways to abstractly break down operators based on the data, then hopefully we can use LLM agents, or I guess even humans, but primarily LLM agents, to now go and implement these new operators that'll hopefully get us better accuracy. And we define a bunch of them in the paper. I'll get into a few of them briefly. And what really excites me about these kinds of rewrite directives is that it's kind of a new optimization space for data systems, right? In the past, like for example, in SQL and relational databases, we had rewrite rules, but these were very rigid rewrite rules. For example, if you see like a filter operation, you should try to do that filter operation as early as possible. These are, in contrast, rewrite directives are very flexible, open-ended rules that LLM agents have to interpret and write based on the data and the task. And the way that our optimizer works is it's top-down. We have LLMs try to instantiate all these possible rewrites. And then to figure out which rewrite is best, then we try to have an LLM as judge tell us, based on sample outputs, which pipeline to use. So I'll talk about each one of these briefly. A common question that we get at this point is, okay, why do you even need something like rewrite directives, right? Imagine a user has this map reduce pipeline, same task we've been talking about on police misconduct, map operation over each document to extract officer names and describe misconduct, reduce operation to kind of group by the officer, summarize and analyze any misconduct patterns. Why do I need any structured rewrite directives? Why can't I just simply give this to an LLM and then tell it to rewrite the pipeline into better scoped operators? Turns out when you do that, we actually did that a couple weeks ago just to verify that indeed the LLM doesn't work off the shelf. LLMs just might not give you a pipeline that is equivalent to what you had in the first place, right? It might not understand the semantics of each operator, right? It doesn't make sense to have a reduce kind of summarizes a group of documents and gives you one output, and then you have a map reduce. Like that doesn't make any sense. Sometimes it will synthesize operations that lose critical details about the documents, and then downstream operators are just inaccurate. But ultimately, right, what's the problem is that you have no control. If you ask an LLM to just rewrite your pipeline as is, you have no idea whether that is going to be equivalent to what you asked for in that pipeline in the first place. So I don't know a better way to say this, but I think that rewrite directives, this kind of scaffold, at least enable some safe operator decomposition where you can at least reasonably trust that the output is going to be the same as before you rewrote the pipeline, or ideally the same. So in the paper, we talk about 13 different rewrite directives, and we have actually follow-up work that is introducing more, so just a more complete set and how to think about that. But broadly speaking, these rewrite directives are in 3 categories, and we call them data decomposition. So think that's just breaking down the pipeline based on the data. We have what we call projection synthesis. Now, this is like a very databasey term, but you should think of this as kind of chain of thought or chain-based decomposition. So if I have a map operation, I can break that down into multiple maps, each map doing a different part of the task. And then we have a couple of interesting LLM-centric idiosyncrasies. For example, if you know that you're doing an LLM-powered reduce, you should pretty much always try to introduce a resolve operator before that to make sure that you are semantically deduping. And again, right, the key takeaways of this architecture here are that these are very abstract frameworks, and they're interpreted by LLM agents based on the context. And depending on how you write a search algorithm to go through these rewrite directives, you could instantiate as many different rewrites as you wanted, infinitely many. So I'll talk about, maybe I'll concretely talk about a few different instantiations. I won't talk about all of these rewrite directives. That would be boring. We would be here for a very long time. So that you can just get a sense for kind of how we're thinking about this problem. So for data decomposition directives, I talked about one before, the chunking directive, where you take the map operation and you rewrite that into something more complex. Turns out we have several that are in this vein. You can read the paper for more, but a concrete instantiation of this might look like the following. So imagine if I wanted to extract all names from a document, what I would do first is split that document into chunks. Then the next thing I would do is have the map operation extract names from each chunk. And then finally, I would have a reduce operation to combine all of the names from each chunk that were extracted into one giant list of names. Now, what is interesting about this, somewhat flexible, right? You don't need to have an LLM-powered reduce for step 3. You could have a code-powered reduce, right? You could just simply concatenate the lists from each individual map. Sometimes you do want an LLM-powered reduce. For example, a lot of times people want summaries on like 500-page documents. Well, in this case, you could summarize each chunk, but then you want a final LLM step to summarize the summaries. So you can kind of think about how you could flexibly kind of adapt this scaffold. So what does the LLM have to do in this case? When we're instantiating something like this, well, it has to devise the new prompt for the sub map operator. Right now that it's operating on a chunk, it has to look at the original map prompt, look at some of the sample data, and then figure out, okay, what prompt should I write to operate on a small chunk? And then the LLM also has to write the reduce operator. Maybe it's a code-powered operator. Maybe it's an LLM-powered operator. Who knows? That's why we use LLM agents. It kind of can figure out maybe what is a good implementation of this operator to get good accuracy. And in practice, this kind of rewrite works really well for these long documents, especially for these tasks when you kind of want to extract every single thing of interest from it. So, extract all names or extract all themes from something, right? If you just feed in your 500-page document into ChatGPT in a single LLM call, it's going to miss a lot of things. And you don't just have to do this for map. We also talk about how you can do this for other operations, for example, reduce operations. So imagine you want to, you have a table of news summaries. So for example, for each city and state, we have some news document, and we want to generate a summary of news articles for every single state. So what happens when you group by state and then create a summary for each state? Again, you might have the problem of, we might be missing certain information, right? Maybe there's some very underrepresented cities in each state that don't quite make it into the summary whenever we're just trying to summarize everything in one state group. So what we can do is first summarize documents for each city, and then think like rolling up those summaries into the state level summaries. Oops, my animations just jumped. I think I was here. Let me verify. Okay, yes. Yeah, so again, right, rephrasing what I said, right, you can drill down into subgroups, summarize subgroups, and then roll up those summaries. And if you use LLMs to do this, then hopefully you will not, you won't miss information from underrepresented subgroups. All right, so in the interest of time, I won't go through the other directives, but you should read the paper if you're really interested. There's a whole world of these kinds of rewrite directives you can think about providing to agents, like breaking down tasks around, into individual steps without even splitting up the data. Talked about how we went through entity resolution. All right. So now imagine that we have kind of all of these rewrite directives that we can provide to LLM agents, and LLM agents can kind of give us new pipelines, new candidate pipelines. Now the question becomes, okay, what's the search algorithm that we use to go through all of these potential rewrite directives? So in the paper, we also propose a search algorithm. So the way that it works is a user submits a pipeline to us. And at a high level, you want to think of, we try to execute the pipeline or parts of the pipeline on samples. If an LLM judge says that the accuracy is good enough, then we don't rewrite it any further. But if the LLM judge says that, hey, you probably missed something, the precision is not good, the recall is not good, then we go and try to rewrite that operator. And you can do this even recursively, right? Nothing is stopping you from combining multiple rewrite directives together. So concretely, what does that look like? One operator at a time. We first run it on a sample to see if the output is good. Then if it's not good, we are going to use our rewrite directives and generate a bunch of different candidate plans and then test them. And then we are going to use an LLM judge, again, to look at sample outputs for each candidate pipeline and tell us which candidate pipeline was the best, replacing the original operator. And like that, you can do this for every single operator in a pipeline. So this sounds like a lot, but in practice, when people write these pipelines in the first place, usually it's like 1 or 2 operators, at most 3 operators, right? So hopefully it's not too resource intensive. Okay, so the key insight here is LLM agents amok, right? Okay, I'm kind of kidding, but the point is that you have LLM agents doing generation, you have LLM agents doing validation, but it's all being done in this very scaffolded, very guided way. So hopefully it doesn't go off the rails. I'll talk a little bit about how we did the validation agents. This kind of is built on some of our prior work that we did on validating like LLM generated data quality. So the idea here is you don't just ask an LLM judge to tell you whether an output is good or bad. You kind of indirectly get it to do so. First, we get it to create an evaluation rubric that is very specific to the task that is described in the operation. So for our police misconduct map operation, this LLM rubric is kind of very tailored to precision and recall. It's derived based on the phrasing and the task described in the operation prompt. So once we have this rubric, then we have the LLM judge basically rank outputs according to this rubric. So it's not just saying, you know, you did a good job, didn't do a good job, as you're ranking, and you're using that to hopefully get you a more precise indicator of whether the plan is good or not. So concretely, you take a sample, take the operation prompt, you have the LLM agent give you this rubric, spits out the rubric, and then the LLM agent goes and applies the rubrics to the outputs as well. And if the output meets all of the criteria in here, then we don't do any rewriting. If not, we definitely do rewriting. I'm saying optimization and rewriting interchangeably in this case. And also in this V1 of this optimizer, we are only optimizing for accuracy. Follow-up work we're doing is also jointly optimizing for cost and accuracy. So how do you improve the accuracy, but do it within a budget? Maybe I'll talk a little bit about this. I think it'll be interesting for folks who are really interested in LLM Judge and LLM pipelines. So some of the things we learned in this process of, creating LLM Judge evaluators are try to design rubrics that concretely get to a decision of good or bad, so true or false. For example, like this was good because it met this criteria. It was bad because it didn't meet this criteria. Every time we tried to do something that was like Likert scale rating, we found that it was very hard to align the LLM judge with our preferences. It was easier to align when the rubric was very clear, binary decisions, and if the LLM judge was doing kind of like a ranking task of, tell us which output best meets this binary criteria. As I mentioned before, infer a very specific rubric, right? Make it concrete, make it have domain-specific checks. And what's nice about us is that we're working on a data processing task. And we know that most people, when they're doing data processing, care about precision and recall in some form. So in our LLM judge that was creating the rubric, we were able to say in this prompt, design your rubric to test precision and recall. And then we gave it examples of that. And then ground evaluation in the data, right? Have sample outputs that are passing the rubric and not passing the rubric, and make the LLM judge come up with those. That seem to work well for us. And I know it sounds very hand-wavy, but apparently that's the nature of prompting LLMs these days. There are tips and tricks to do it, so this is just what works for us. All right. So now in this optimizer, imagine that we are definitely rewriting a pipeline. So here's our pipeline. We have decided that this first operator needs to be rewritten because it is not good on a sample. So how do we come up with the specific rewrites? Well, that's how we use it. We use our rewrite directives to do this. We just find all matching rewrite directives and have LLM agents synthesize candidate pipelines. Now, what is interesting is when it generates a new candidate pipeline, it's generating entirely new operators. Right? That's the nature of our rewrite directives, taking one operator and making it multiple operators. So when it synthesizes a new operator, we recursively check, hey, should we rewrite this operator or not? Like, is it good enough as is or not? If it's good, we don't really do any rewrites as per our original algorithm. Sometimes it's not very good, so opportunistically, we go and rewrite that operator. And we kind of do this recursively until some maximum depth of 3 from the user's original pipeline. We found if we didn't have a maximum depth, then the agent will just continue rewriting for as much as it wants, as deep as it wants, and never stop. So it was a little bit of an arbitrary decision that we made, but I think it goes to show the nature of these optimizers, and if you're writing algorithms for them, you very much need to scaffold the exploration that they do. So these checks here mean that the operator is good as is, and then it doesn't engage in any further rewriting, deeper rewriting. And you can imagine we get hundreds of candidate pipelines this way, depending on how many different variants of each rewrite directive you want an LLM agent to implement. And then once we have all of these candidate pipelines, we go back and use our LLM judge prompt, a rubric that we created, run each of these candidates on samples, and then try to come up with the best one based on that rubric. And then we have some optimizations for kind of how we do the ranking. Right? If we do pairwise comparisons, that'll take us forever. So check out our paper to figure out how we do that a little bit more efficiently. All right. So with that, you basically traverse through the entire pipeline, rewrite it, and hopefully your pipeline is more accurate. And we found out in our experiments out of the box that it got us pretty good accuracy improvements, which I want to stress, it was very exciting to us because we don't provide any ground truth data, right? We literally provide the documents. We just say, here is our task. Now come back to me with a more accurate pipeline. And it did. Sometimes it was only a little bit more accurate, and sometimes it was a lot more accurate. Actually, in our case study, it went up to be more than 200% accurate, which is very exciting. So read the paper for specific numbers there. I think that, at least, so 2 things actually I want to talk about here. One is we really have a first pass implementation of these rewrite directives. I imagine that you can do a very good job prompting the LLM agents to follow rewrite directives very well, and that'll get you even more accuracy improvements. The other thing is this really motivated kind of cost reduction for us, right? So when you do break down these tasks into smaller scope operators, you do end up paying more, right? Because you have more LLM calls. So some follow-up work that we're working on is, how do you do this cheaply? How do you search for cheap and high accuracy plans? I will skip the rest of these. Again, just numbers, check out the paper. And with that, maybe I'll spend the next 5 to 7 minutes going over the DocWrangler project, which is a follow-on. And then we can take questions later on. All right, so I'm going to get into DocWrangler. Now, when we released DocETL, the open source version, we had some people using it, and that was very fun and exciting for us. And the issue that we found when people were emailing us or telling us their experience about it, or even just in user studies, was that they had to build some sort of human-in-the-loop iterative process to arrive at the analysis they wanted. And as a researcher, right, this is an interesting problem because the intent is there, right? They know the data that they want to query, and they know what they want to query, but they don't know how to specify it in the way that the LLM can understand. And sometimes if they think they know what they want, they go and see what the LLM generated and then realize they want something slightly different. Now, all of this is a very rich human-in-the-loop problem. So we set out to ask the question, okay, what would it be to build a playground-like interface for people to prototype DocETL pipelines? And the case study that we really grounded the DocWrangler work in was a collaboration with the Scottish Climate Intelligence Services. And a very, again, similar problem to the police misconduct setting, but it's not police misconduct, it's climate reports. And they want to extract common themes and ways for which, companies and regions are doing climate interventions. So for example, maybe an intervention will be to implement a bike scheme or implement like new credits for ride sharing, for example. So they wanted to extract instances of these and then do some analysis to see what are common ways that companies and regions and areas are trying to improve the climate. So the IDE that we prototyped for people to prototype their own DocETL pipelines looks very similar to kind of, if you're familiar with notebooks, if you're familiar with Wrangler or data transformation interactive tools, we kind of try to mash up what we've learned from pretty much the last several decades of these kind of data transformation tools. The IDE has two components. There is an editor for the pipelines, which is kind of like a notebook. And then there is an output viewer. So take a look at the DocETL outputs, and you can visualize them like histograms of each attribute that we extract. You can drill down into individual ones. You can also view statistics on the original documents and data, so forth. So that was where we first started with this interface. We gave it to people and we said, does this help you? And it did to some extent, but there were some challenges that we could not have anticipated, and we ended up having to design custom solutions for. And we framed these challenges as interaction gulfs in semantic data processing. And if you're an HCI researcher, you might be very familiar with Norman's gulfs. So we take the gulf term literally from the history, but we designed we come up with 3 new interaction gulfs for our task here. And broadly, they're between the user who's writing the pipeline, the data that they want to run the pipeline on, and then the pipeline, of course, that they are writing. So I'll talk about the first gulf, the gulf of comprehension. Now, we find that everybody who's writing a DocETL pipeline, they don't know everything in their data, yet they still have to write a pipeline to operate on it. So sometimes when they run on their data, they learn new things about their data, or they learn new things based on LLM outputs that will inform their analysis. So this gulf of comprehension is basically how can the user figure out everything that's going on in their data to basically write the best pipeline. So I'll skip this part a little bit. I think I already mentioned that. Users need to make sense of the data so that they can write the correct prompt. So the solution that we built in DocWrangler was an ability for users to keep track, basically write down notes on any documents, any outputs, any LLM behavior, and try to do this in situ. So when they're looking at the output table at any time, they can click on something, provide notes on it, and they live persistently in a sidebar. When they're looking at their data, same thing. And interestingly, we built like chatbots and other AI assistant tools that can read from these notes. And these notes really provide other contextual information for the user and for any downstream analysis that they want to do. So what that kind of looks like, maybe a user expands on something in DocWrangler, some attribute that they've extracted. They provide some notes. They decide that they want to add them, and they live in this persistent sidebar. So that helps us with this gulf of comprehension, just keeping track of everything that's going on in the data. So just knowing what's in the data is not enough, we realized. Even if you have all of these notes and you know now exactly, specifically what you want to query, writing that prompt is the second hurdle. So this is what we're calling the gulf of specification. User intent is very well known, but writing this in a very specific prompt, right, specifying this task in English in a well-structured way for the LLM to understand, in a detailed way, because we know today's day and age, these prompts have to be extremely detailed. This is very hard for humans to do by themselves. So our solution that we built for bridging the gulf of specification is what we call prompt refinement. Now remember, we already have these notes from the gulf of comprehension, these observations that users have taken. What we can do is provide a conversational interface to use those notes and automatically propose prompt edits. And that's exactly what we do. Anytime the user wants to improve their pipeline or update their pipeline based on any notes that they've taken, they can click a button. It will take them to this conversational prompt improvement interface. They'll get suggested a new prompt. They can even iterate on that. And then when they're happy with it, they can finally put it back in their pipeline and rerun the pipeline. So that checks the box for the Gulf of, well, it doesn't check the box, but that is a solution to this Gulf of specification problem that we observed. Now, the last problem that we observed in this was what we call the Gulf of generalization. So this means even if you write a very, very specific prompt that's very detailed, and a human would take that and learn how to figure out how to do that well, doesn't mean the LLM can do that correctly, because LLMs are error prone. As we observed in DocETL, somehow we have to be able to know when they're error prone and then fix it, rewrite it in a way so the LLM understands. And so the solution here was basically plugging in DocETL, but in an interactive way. So assisted operation decomposition. So we notify users when we think the operation is too complex, and this just uses DocETL under the hood, and we give some rationale for why, and then users can engage in kind of this decomposition themselves. So they might see the notification, they might see the rationale for why it's too complex, and then they click a button to say, okay, rewrite my pipeline, and then they can see the logs transparently, like from the LLM judge and all of these components under the hood in DocETL, and then finally see the new rewritten pipeline. So overall in this DocWrangler project, the main purpose was build this IDE. We learned a lot of new interesting things along the way, came up with this 3 gulfs model. It came up with targeted features for each gulf. And we also have a bunch of user studies, both like in-person rich user studies, excuse me, as well as an online deployment where we shed more details on kind of how people use the tool, how people develop strategies for semantic data processing. For example, they added new attributes that were not exactly what they wanted to query. Say they wanted to extract names or they wanted to extract medications from transcripts. They would also add these reasoning or explanation attributes to go over them at a high level and then feel confident, oh, okay, the LLM understands what I mean. Now, nobody knows under the hood whether this actually is accurate, right? The LLM actually used this reasoning or not. But it was interesting, I think, that people really cared about this and really repurposed the tool in a way that helped them feel confident in the analysis. And a bunch of different strategies like that we talk about in the paper. Encourage you to read it if you're interested in this area. All right, so the last thing, so I promise I'm on the last slide now. So I know it's been a really long session and we'll definitely have time for Q&A. But hopefully this was a good like whirlwind tour of kind of what motivated us to start DocETL and the class of problems that we try to target, some of the very rich research problems to explore in the area around writing good pipelines, query optimization, even HCI problems, AI problems. I think it's a very exciting area for the next several years of research. But if you take any takeaways from this talk, we are working on some follow-up projects. Some of them are already under submission. For example, the jointly optimizing for cost and accuracy. I mentioned before, like how do you do DocETL-like rewrites, but do this when users have a budget for the pipelines that they want to run. How do you kind of figure out how to make adaptive execution plans on the fly? So one of the things about DocETL right now is we come up with a plan that's applied as is to all documents in your collection, but sometimes you want to apply different plans to different groups of documents. So kind of maybe you could use cheap models to do these. Maybe you could just have these dynamic plans, and how do you come up with them is also an interesting problem that we've been looking into. And overall, in this talk, hopefully you are all convinced that semantic data processing is an exciting and an emerging new area powered by LLMs. I think it's going to be exciting in the future as well. Care a lot about accuracy, not just cost. I think that's going to be a mindset change for a lot of systems researchers here working on these problems. And I'm very excited by the promise of the agentic optimization. I think it's a very rich space of optimization. As LLM agents get better, we'll hopefully even have better rewrites of pipelines that just automatically come up. And with that, thanks so much for having me. You can feel free to email me if you have any questions, and you can find me on the internet.
Wow. That is a cool tool.
Thank you.
I'm super impressed by this. And one of the things that really stuck out to me was how like users like the little rationale or explanation that's given. It reminded me a lot about how like Uber, one of the reasons it really kicked off and people liked it was because it showed you where the cab was. And like
Yeah,
even if that was inaccurate, it's like, oh, now I have this sense of like certainty about it.
I think it's so interesting too because we didn't design the tool that we never anticipated it, and yet half the people in the study were like, "Oh, let me check. I don't know if this is correct. Like, let me just do this and see if it's correct." And it was like, I would never have thought of that. Super interesting.
Yeah, that's the thing about users. They're all like kind of weird. Um, we have a bunch of questions in the chat, but
Yeah,
selfishly, I had one to kick us off
sure.
because this kind of study group I'm working with is thinking about AI adoption in businesses.
Mhm.
And one of the prompts we've been asking ourselves is when big data came on the scene, the whole sacred cow that was killed was like big data happens when data is cheaper to store than to decide
Mm.
what to do with. And do you feel like there's another kind of paradigm shift with data and how people should think about it today?
I think there's a capabilities shift, which is you have the large language model to now execute arbitrarily complex tasks. That's like one huge shift that I think we're seeing already happen. Like data warehousing companies, every single one of them, Snowflakes, Databricks, BigQuery, they have the ability to write these kinds of like semantic operators. Snowflake has like an integration with DocETL where like you can just like run these on your entire data warehouse and it'll cost you an arm and a leg. You have no idea whether it's accurate or not, but people are still doing it, which I think is so fascinating. So maybe that is a paradigm shift. But I think what's an exciting research challenge for us is, okay, how do you actually get business value of it? Maybe similar to, just because you store data doesn't mean you just get business value. It's just now people are paying for it. And now we have to figure out why they should continue to pay for it forever.
Yeah. Okay, I'm gonna pull up some questions from the chat. We can just kind of you can fly through them however quickly you'd like. First one from Patrick. How would you characterize the differences between this project and Stara out of Stanford?
Stara, I have not heard of Stara. Um, I'll have to look at that. It looks like it's a research assistant. Okay, I'll have to look into that. I have no idea what that specific things. But broadly speaking, one difference between kind of how we're thinking about this project and I've seen other AI-powered like data analysis projects are like we're trying to be agnostic to any task, right? We're thinking about like what is the infrastructure layer going to look like how are people going to specify pipelines? And there's nothing specific to climate or like law or medicine or whatnot. And that's a very, I think, database ethos, right? Like build a system and then have like other people kind of tailor it, maybe even have like applications that are built on it that are commercialized as well.
Nice. Next question from Robbie. Are there metrics on how DocETL improves results versus directly using LLMs? For example, hallucination reduction count. I imagine that this is like several orders of magnitude difference, just naively.
Yeah. So hallucinations actually have been improving over the last year. LLMs hallucinate less. What I will say is the order of magnitude improvements is on recall that we get. So LLMs now are trained not to hallucinate as much, but they also don't give you much as a result. So we can get a lot better recall with our rewrites. If you want specific numbers, you should definitely check out the papers. We report hallucination rate. We report like pretty much all of these fine-grained details. And you can also check out the website, docetl.org. This is like, we have a case study on there of, just comparing extraction to like Gemini and showing how we get orders of magnitude more extracted.
Awesome. This is a nice one from Michelle. Are there different skills I need to use DocWrangler at scale, which I don't need when I'm working with just 100s of documents? In other words, will my playground experience scale to production of 100,000, million, 10 million plus documents?
Love this question. I think we are seeing that we need another tool for this. DocWrangler at scale or LLM at scale. So the scale is obviously going to be different for different people. I think there's like 100 document scale, which is like great for DocWrangler, maybe even 1,000 documents, depending on the size of documents. But there's like another point at which things break that we're seeing around like 50K, I would say. And I think what's happening is that there are like new clusters of documents that emerge at that scale that people are not seeing when they're prototyping in DocWrangler. And now I'll give you an example of like court opinions. I saw this data set of court opinions. Most of them look the same. Most of them are at the federal level. And then once you get to a very, very big scale, sometimes you're getting outliers. Now you're getting state level. Now sometimes you'll just have the same court opinion that's like duplicated 100 different times. You see like all these crazy data quality problems that you didn't see, not just data quality, but just new types of data you never anticipated. And I think we're going to need a different tool to like help uncover these new clusters and like resolve them on the fly. So
Yeah, it does seem like there are two distinct use cases. One of the things that really got me onto LLMs initially was I saw a couple of paramedics on Reddit saying how they use it to like search for protocols in a database because their policy books are so big that they can't remember anything. And like the trade-off of even accuracy versus the speed there was worthwhile. Versus like 10 million documents, you're probably doing something completely different.
Yeah, it's very, and the time that it takes to execute at that scale is also so long. So you can't easily design an interactive experience around that you could have with, say, like hundreds. And I think therein lies is like a very interesting research opportunity.
Here's one from Venkatesh. DocETL seems like a meso level of AI between micro level model improvements and org or macro level strategies and philosophies about AI usage. What are the unique challenges of working at the meso level of abstraction?
This is a nice question. So I'm going to try to answer it, but please follow up if I didn't answer it. So I'll say I started the project thinking I want to stay in a particular lane, which is I don't want to make changes to the model. I'm going to assume that models are going to get better. And I'm not going to assume things about the data. Like I know real world data is messy and organizations have like very bespoke ways of handling the data. What does it look like to build the system or infrastructure layer? And I will say, as everything has evolved, I'm realizing that organizations are changing. So for example, with the public defenders, people's appetite for AI is growing, and I need to adapt to that. People's tolerance for errors is also growing. And so all of the like kind of rigorous checks we would have to do, we would have to like employ student interns and so forth to check whether outputs are correct or not. We don't have to do that as much now. And I don't know how to design the right, I guess the real challenge that I'm describing is how everything is changing and like what we're building has to kind of accommodate for people changing, organizations changing, models changing. And sometimes we have to be flexible and go into the layers that we didn't expect. So for example, models are changing in a particular way. I don't think they're changing for this kind of large scale data extraction. They're changing in a way that's optimized for conversations. For example, KV caching and LLM serving. And that is very, the KV caching policies for LLMs are very different from how you would want to do, very different for conversational AI, how you would want to do it for large scale data transformation. And I don't see anybody working on this problem. So now we have a little working group where we're thinking about this problem. And I never wanted to get into it in the first place, but here we are. So TLDR, I think it's just, we have to adapt and be aware of all the challenges and be willing to get our hands dirty when we didn't expect.
Yeah, I imagine that making any tool in this space is very much not, there it is, even less so than it was like in the early software days where you actually bought disks.
Yeah, I don't know. I'm not that old.
No, me neither.
I wasn't around in the 70s, 80s, but I can only imagine.
I certainly was not either. Have you tried using this approach to specify logic operators in law, code, and regulations? thinking about translating dense legalese into Boolean operators.
Yeah, I know a couple of people who are using it for law, legal, even like realistic, any contract law, for example. This is a great application for, but law is a great vast domain. So I'm sure there are many, if we really dig into it, I'm sure that there are like new types of queries that you could like develop specialized optimizations for.
I know we're at time, but one last kind of provocation or question here for you. I noticed that the pipeline kind of has this recursive element to it. So like it's continually evolving as people use it. And how have users responded to that versus like a more rigid thing that they know how to deploy every single time?
I see. Is what you're saying, like LLMs may change under the hood, so like the behavior is not predictable, like as you're continually running this, or
Yeah, both that and kind of at a higher level, it seems like you need to update things at parts of the pipeline.
I see with new data.
Yeah.
Yeah, that's hard. I don't think we have a great solution for that yet. Where we've seen the greatest success for DocETL is like you just try to run it once or twice on a very large corpus to give you like structured information that you put into a relational database and then query or like use for RAG or like a chatbot or something like that. Like people love that. I think it's for real ETL, which was the original dream of the process, where you want to recur like in a basically every week or something, like transform your data. I think it's hard for the reasons that you said. We don't have a good solution, and especially with unstructured data, right? ETL for structured data was already hard, already spawned many billion-dollar companies, still are active. But we have good ways to think about, you know, structured data quality, structured data outliers, how to adapt to new outliers as they come in. We don't know how to do any of that for unstructured data. So I think, again, a great research problem if folks are, I don't know, mining research problems. I'm excited to kind of tackle that.
Yeah, it seems like there are kind of an infinite pool of research problems here. And I think they can follow the work on DocETL at docetl.com, and they can follow what you're doing at Shreya.com. That's with a hyphen, SH-REYA.com. And thank you for coming on the town hall.
Yeah, thanks for having me. And thanks for the great questions, everyone. Appreciate the engagement.
Okay. Bye, everybody. And we will see you for the fall series, which is happening soon. We'll have a special host, hopefully. And this is a year-round track. So just because the summer series is over, don't miss out on the fall series. And for those in the protocol school, we have a case competition overview right now. So I'll see you there to give a brief on that and point you in the right direction. Bye.